Another microscopic property of atoms is the ionization energy. That is, the energy required to remove an electron from a gas phase atom to produce a gaseous ion. The removal of the first electron is called the first ionization potential, or ionization energy, which is usually abbreviated IP. The removal of a second electron is measured by the second ionization potential, and the removal of the nth electron corresponds to the nth ionization potential. The relationship of any two adjacent ionization energies can be deduced intuitively. For example, the first ionization potential has a smaller value than the second ionization potential because the second electron is being removed from a species that is positively charged, which should require more energy than the removal of an electron from a neutral species. The first ionization potentials for all the elements are known and are presented in this periodic table-like chart. Although it is possible to discuss trends in the numbers as they are presented in this chart, much greater insight is to be had by plotting the values of the first ionization potential of an element against its atomic number. First, note that the ionization potential across a period generally increases from the first member in the period to the last member. This increasing trend becomes less and less steep from one period to the next. The trend in period 4 between calcium and copper, where the 3D orbitals are involved, appears almost flat, which suggests that the increasing nuclear charge for these elements does not have the usual effect on the outermost electrons, which are 4s electrons. The ionization potential trends down a given family is illustrated by the dotted line drawn through the data for the rare gases helium, neon, argon, and krypton. This decrease in the first ionization potential is to be expected even though more protons are added to the nucleus as one goes down a family. To get from one member of a family to the next requires the addition of positive charge and also the completion of a full energy level. So, although there is more positive charge in the nucleus, it is apparently screened by the electrons in the completed energy levels, so that nuclear charge is not as effective as it would be expected from going across a period. In general, the trends in ionization potentials also can be interpreted on a microscopic level using our wave mechanical nuclear atom model. Trends in other microscopic properties can be correlated with the general wave mechanical nuclear atom. As an example, consider the process called electron affinity, which is the energy involved when a gaseous atom acquires an electron to form a gaseous anion. The data for some of the elements are shown in this periodic table-like arrangement. Inspection of the data shows the trends depicted in the smaller periodic table diagram. That is, the electron affinity becomes more negative going from left to right in any period. The electron affinity becomes more negative going from bottom to top within any family. One final microscopic property will be considered here, namely the electronegativity of a chemically bonded atom. The electronegativity of an atom is a measure of the ability of an atom involved in a chemical bond to attract electrons to itself. Electronegativity can be measured experimentally in a number of ways, and it can also be estimated from theory. The historical unit of electronegativity is the Pauling unit. Fluorine is the most electronegative element with a value of 4.00 Pauling units. The Pauling unit was named after Linus Pauling, who was the first to devise an electronegativity scale based on experimental data. The electronegativity increases from left to right across the period, and it increases from bottom to top within a family. These trends can be understood on the basis of the wave mechanical nuclear atom model, incorporating increasing nuclear charge from left to right in a period and from top to bottom in a family. The increase in nuclear charge from top to bottom in a family or group is modified by the creation of successive intervening filled orbitals which drastically modify the nuclear charge effect. We have seen that Mendeleev's original ideas about periodicity, based on careful consideration of the physical and chemical properties of atoms, can be extended to microscopic properties of atoms by an application of the wave mechanical nuclear model. The variables are nuclear charges and the screening effects of filled intervening energy levels. Some of the microscopic properties we have discussed in this unit were not related to any of our previous work in this course. They were just obtained from the literature to prove a point with respect to the periodic table of the elements. These properties, atomic and ionic radii, ionization potentials, electron affinities, and electronegativities, will be revisited in future units where they will be discussed more thoroughly.